Hey everybody, Jared here from Abstract, and in this video, I'm going to show you how you can create and deploy your smart contract accounts to the Abstract testnet to showcase its native account abstraction feature. I'll first walk you through how Abstract actually implements native account abstraction, meaning there are no EOA wallets on the Abstract chain, how that works under the hood, and then move into writing out your own Solidity smart contracts and deploying them to the Abstract testnet. By the end of the video, you'll submit a transaction that is initiated from a smart contract account that you've built and deployed to the Abstract testnet. All the links to the source code will be in the description. You'll also find a link to a Discord server where you can get help if you get stuck at any point. Without further ado, let's jump right into it. Before we get started, I want to show you a couple of dependencies that you'll need to have installed, how to check if you have them on your machine, and there will be links in the description below for you to go and find them if you don't already have them. The first thing you'll need installed is Node.js on your computer. You'll need at least version 18 to follow along with this tutorial. Second thing you'll need is Docker. You'll need Docker installed and actually running on your machine. We're going to be using this for our local node just to deploy smart contracts and test them out on a node running on our machine. And if you're in a Windows environment, I like to use Ubuntu with WSL, and I'll quickly show you how to check if you have that and how to install it if you don't already as well in this tutorial. The CLI that we're going to use is not recommended to be used on a Windows terminal, so I would strongly recommend if you're on a Windows machine, install WSL, and I'll show you how to do that quickly before we dive into it as well. Okay, so if you're on Windows, you want to check if you have WSL, and if you don't, it's actually the same command. You can just do -- install, and for me, I already have the Ubuntu installed on my machine, so it's just going to swap into this Linux environment where we can run Linux commands, and it's going to act as if it were a Linux environment for the CLI that we're going to use as well. Then for Node.js, you can just do node-v. You can see I've got v 20.10 installed. And for Docker, you can do docker-version to check if it's installed. And you want to make sure that it's actually running. So you can do docker info, and that will print out if it's actually running on your machine. So if you've got all of these commands set up, you're ready to actually start the tutorial and create our first project. Since Abstract is built on the ZK stack, we're going to use the ZK Sync CLI to actually create our project with Hardhat and Solidity and a simple smart contract to get us started. First thing we want to do is npm install -g for global ZK Sync -CLI. Once that's done, you can just make sure you're on the latest version by running npm update -g, again, ZK Sync -CLI. Since we just installed it, this shouldn't need any updates since we're already on the latest version. Then we're going to run the create command from this CLI that we just installed. So we'll do ZK Sync -CLI create. And this is first going to ask us a couple of questions. So it's going to ask us what directory do we want to initialize this project in. Let's just say native AA demo project. We are going to be creating a contracts project. So this is a smart contract project, not a front end. So we'll go ahead and select contracts. We'll do Ethers v6 just to grab the latest version. And I'm going to be doing Hardhat plus Solidity here. Now for this step, it is not best practice to ever paste your wallet's private key into anything really. You should never put a wallet private key in plain text like this. For simplicity in this tutorial, I'm just going to go ahead and paste a private key of one of my test accounts that has no real money. It is a brand new account that only has funds on the Abstract testnet. This has no real money associated with it and will never have money associated with it. I'm not going to go too deep into why private keys should never be put into plain text, but never put a wallet that has any real money or will ever have any real money in plain text like this. This step is just required for us to run the deployment script to deploy our smart contract to the Abstract testnet. So what I'll do for this video, but you can do the same if you have no real money in your wallet, but the best practice is to use other means to actually access your private key. But for this video, we'll go ahead and paste a test account's private key into this option here. And we'll go ahead and select npm for our package manager, and that's going to go ahead and create the project and install all of the dependencies on our machine. Great, and if that process is successful, you should see a little screen that looks like this. And the first thing we're gonna do is copy this change directory command to swap on over into that project. And for me, I like to open it up in Visual Studio Code just to see what we have with our fresh new project. Okay, so bringing the project up, you'll see we have a contracts directory with some sample smart contracts for an NFT, a fungible token, a simple kind of hello world greeter smart contract, and some paymasters. So the first thing we're going to do is actually just clean this all up to give us a really bare bones setup. So I'm going to go ahead and delete these 3 folders here, the ERC20, the NFT, and the paymasters. We'll also go ahead and delete our test folder here. And then again, within the deploy folder here, we'll go ahead and do the same. We'll delete the ERC20 folder and the NFT folder. And now just to give you a quick understanding of our starting point, we have a simple greeter smart contract that has a variable in state that you can read and update. And then within this deploy folder here, we have 3 scripts. So these are actually hard hat scripts. The first one is to deploy the smart contract, as the name suggests. So it grabs the contract by its name, provides the constructor arguments, and then runs this deploy contract script found in utils, which I'll show you shortly. Second, we have this interact script. So once we have deployed the smart contract, we can then interact with it. So what we need to do in this flow is paste the smart contract address that we just deployed from the deploy script into this contract address variable here. And then this will go ahead and do whatever logic you want within this function. So for us in this kind of template, it seems like we first read the greeting, we then set the greeting, we wait for that transaction to get mined, and then we reread the greeting variable to hopefully see the updated greeting that we set on line 28 here. Then within utils, we have a couple of helpful things within here. First, we have a get provider function. So this is going to grab all of the information essentially about what network we have configured inside of our hard hat config here. The second thing we have here is get wallet, which is very similar to get provider. However, get provider just provides read access through the RPC, whereas get wallet provides write access through a wallet. And on line 32 here, you can see it's actually initializing that wallet either with the environment variable from wallet private key, which is populated with the private key that we input into that CLI initialization step if you chose to actually paste it in there. Beneath this, we have some helpful functions like verify enough balance to actually perform some action. We have the verify contract, we have deploy contract. So these are obviously going to be used when we deploy and verify our smart contracts to whatever network we're deploying to. And then finally, beneath that, we have a list of local rich wallets. Now, this is why we wanted to install Docker on our machine before we started this process, is because what we're going to do just in the kind of local development phase is we're actually going to run a local node that's kind of hosted inside of our Docker containers. And each of these accounts listed in this array here are pre-populated with tons of ETH on that local node. So you can see each of these accounts, and you can easily access and submit transactions to and from each of these accounts are going to be preloaded with tons and tons of ETH on that local node network that we're going to run and deploy our smart contracts to initially. So what I'm going to show you now is how to run a local node inside of a Docker container, and we'll compile and deploy our smart contracts to that local node. This is why I got you to install Docker and run Docker if you haven't already, because we're going to actually initialize this local node inside of a Docker container. So if you open the package.json folder, you'll see in this script section a couple of scripts. So we have clean, we have compile, deploy, interact, and test. So since we kind of deleted all our tests, I'll just remove that from the video for simplicity. So what we're going to do is clean, compile, and deploy, and then interact with our smart contract inside of a local node. But first, we actually need to kickstart that local node so we can deploy to that node. The way that we do that is from the terminal, we can run zksync-cli dev start, and you'll want to select the option that says in-memory node. I've already configured that with zksync dev config. So if you want to configure this, I think the default is actually in-memory node, but you'll just need to run config and then rerun that start command. So then, just to confirm that's actually working, you can jump into the Docker containers here, and you can see ZK CLI in-memory node should be running as a container. Now what we're going to do is we're going to actually compile and deploy this simple greeter smart contract. So if we swap over to the terminal again, all we need to do is npm run. Optionally, you can do clean first just to clear out any pre-existing deployments or compilations that you already have. Often I like to do that just before I run the compilation process to make sure I know no funky business is going on under the hood. Once that's done, you can do npm run compile. And if we swap over to our VS Code, once this command completes, what we should be able to see is these two folders get generated, the artifacts DK and the cache-zk. So you can have a little quick explore around here if you want to, but what you'll find is you get the ABI of your smart contracts, and down here, you'll get the bytecode of the smart contract. So that's essentially what we're doing, is just compiling our Solidity into bytecode with that command. Then what we're going to do is, before we run the deployment script, we need to jump into our hardhat config and see where we're actually deploying to. So here you'll find a list of networks such as the zk-sync Sepolia testnet, zk-sync mainnet, Goerli testnet, Dockerized node, and in-memory node. So hopefully your kind of alarm bells are ringing and saying, well, I just ran the in-memory node from the zk-sync CLI from the terminal. I'm just going to go ahead and set this default network on line 6 to be in-memory node. So what we're going to do is we're then going to jump back into the terminal. We'll clear this out and we'll run npm run deploy. So now this is pointing to our in-memory node, and it actually fails because this account that I set up as my private key has no funds in it on the local node. But hopefully you remember, inside of the initial setup, inside the utils folder, if we scroll down, we have a bunch of rich accounts that have funds preloaded for us to actually use and deploy smart contracts to the local node. So we can just grab this private key, for example, and then inside of our environment variables folder, or environment variables file, the .env, we can just paste one of those example rich accounts, which has preloaded funds on the local node. And if we swap back into the terminal now, just rerun that command, and we successfully deploy our smart contract from the account that is set inside of this utils file here. So this deployment actually came from this first rich account instead of the original account that we imported into the environment variables. The only reason that you would need to put your private key in for a testnet deployment is if you plan on actually taking this beyond your local node. So whenever you're ready to change your deployment from a local node to a testnet, such as what we're going to do in this video with the Abstract testnet, that's when I'll swap on over to an account that I control, but obviously has no real money, as we're not going to use an account that has any real money associated to it for this deployment process. One final thing you'll notice after your deployment is that we get a new directory again called deployments-zk, and you can see what we've actually deployed and where we deployed it. So you can see the chain ID as well as, again, the ABI and the bytecode that we actually deployed to that in-memory node that we're running inside of our Docker container. The final step of this process, and the reason I'm showing you this is because we're going to be doing this a couple of times throughout the video. So I want to show you the general flow before we start diving into building our smart account, is when we see the terminal command complete for the deployment, we can see a contract address here. So Greeter was successfully deployed at this address. So what we can do is actually go ahead and copy this smart contract address, swap on over to VS Code, and then in the interact.t file, on line 6, let's populate that variable with the address of the smart contract. So this is basically saying, well, interact is a generic script to perform these actions. It's not that generic, I guess, because it is currently specific to the Greeter smart contract. But what we can do is, since we populated line 6 now, we can jump back into the terminal and clear this out. We'll run npm run interact, and this is going to run the interact script. And you can see what's happening here is pretty much walking through this file. So first we console log the interacting with this script. We grab the Greeter smart contract, We initialize it with a wallet. So this is interacting with the wallet that we saw in that util script for the get wallet function. Just quickly show you that again. So it initializes a function based on the private key here. It then calls the greet smart contract function, logs out the output, calls the set greeting from the wallet, and then rereads the value. So from the terminal, we can see that all reflected. It logs out, hey, I'm interacting with this. The current message is reading that from the smart contract, initializes a transaction, waits for it to get mined, and then prints out the new state variable as hello people. So what we can do just to show you kind of what's going on, to make it even clearer, let's say hello YouTube here to make a quick change on line 28, swap back into the terminal and we'll rerun that. Should see it starts out as hello people and swaps on over to hello YouTube. So this is just a quick example of how you can interact with the smart contracts that you deploy. What we're going to talk about for just 1 or 2 minutes before we dive into the Solidity code is something pretty exciting that is unique to the Abstract protocol and is different if you've ever built on Ethereum before. So we'll quickly explain 3 key concepts that are essential for us to understand before we dive right into the code. Those 3 concepts are the system contracts, the bootloader, and the default account. Now, these kind of sound scary, but we're going to walk through each of those individually, and then I'll show you a diagram that really helped me solidify, okay, this is how this full process works together and how these pieces of the puzzle kind of play each role in this system. The first part is system contracts. So Abstract has these special smart contracts that have specialized privileges to information about the protocol that are deployed at Genesis. Okay, so as soon as the protocol or the chain started, these smart contracts existed to perform some feature or functionality of the chain. There are numerous system contracts. 2 of them are the next 2 points and concepts that I wanted to cover. One of those system contracts is called the bootloader. So that is our second point. The bootloader is a special system contract that handles processing of each transaction in the protocol. Okay, so every transaction goes through the bootloader first. The third concept that I wanted to introduce is another system contract called the default account. And I'm going to jump into the diagram to explain how this works and why it is a piece of the protocol. But first, a concept that I want you to keep in the back of your mind is that there are no EOA accounts in Abstract, but you can still use EOA wallets. And that is confusing and took me a while to get my head around, but I'm going to show you a diagram now that hopefully clarifies what that means. Okay, so as I said, the first point is that Abstract deploys multiple system contracts at Genesis. One of those system contracts is the bootloader in blue here. So first concept, system contracts. Second concept, bootloader. Third concept was default account, and we'll get to that at the bottom left here. So to show you how these pieces of the puzzle fit in and why this is even important is because it is somewhat different from Ethereum. It has a similar flow, but different pieces of the puzzle and a different way of handling transactions. So let's start at the very top here. Transactions go into the protocol and reach the bootloader. I put a little note here, as this took me a little bit to kind of grasp, is that transactions don't necessarily have to come from a wallet. This is something that kind of tricked me at first, is the process or the idea of submitting a transaction is that it comes from a wallet, but it actually doesn't necessarily have to. I could submit a transaction via the RPC, and it doesn't have to come from a wallet. I could just write a script that sends that transaction. The reason it typically comes from a wallet is because of the signature that you generate from your wallet's private key. However, as we'll see soon, that is actually not required in this protocol. It might be required, but we'll see in what circumstances and situations that it is not. So one thing that kind of tricked me is you actually don't need a wallet to submit a transaction. Once a transaction gets submitted to Abstract, again, it has these system contracts. One of them is called the bootloader. And as we mentioned before, the bootloader receives every transaction. The reason the bootloader exists is because not every EVM opcode is exactly the same in Abstract, at least at the time of making this video. Okay, so some opcodes are not kind of optimized for zero-knowledge proofs, so they've been abstracted away into system contracts that kind of handle them in a ZK-friendly manner. One of those system contracts is the bootloader. Bootloader receives all transactions and processes them in batches of transactions. So what it does is it takes multiple transactions and it looks at where did this transaction come from. What it does with that information is it takes the from address from each transaction and sends it to that address. Okay, so let's say the from address is OX123. It sends it to OX123, which is a smart contract because every account on Abstract is a smart contract. So let's go through one flow here. I used my Coinbase wallet here in the top right. I submitted a transaction to Abstract. It comes into the bootloader. Why does it send it back to my account? That doesn't really make sense. So why does the bootloader take the transaction, send it to the address that I just submitted it from? Let's go down this middle path here. So it takes the from address, which is my wallet address, OX567 or something like that, and it reaches my account. So my account is a Coinbase wallet. It's an EOA. How is there no EOAs in Abstract? So what it does is when it says smart contract account, it sends it to OX567, the account that it came from in that transaction information submitted via the RPC. Once it reaches OX567, the protocol makes a decision here and it says, is there any contract code deployed at OX567? If there is not in this red path here, it uses the third concept I want to introduce called a default account. Okay, so if there's no contract code at the address it sends it to, it assumes, okay, that's an EOA. There is no contract code deployed here, such as a smart contract wallet that we might deploy. So I'm actually not going to treat it as an EOA because there are no EOAs in Abstract. I'm going to treat it as a default account smart contract. Now, the default account is literally a smart contract that handles transactions exactly the same way that an EOA would. We'll talk about why it's handled that way shortly, but the other alternative is if it reaches OX567 and there is contract code deployed there, then it goes through the process of saying, okay, let's treat this transaction according to how this smart contract is built and coded to handle transactions, which is what we're going to build in this video. We're going to go down this green path to say we've deployed a smart contract at OX567. We'll submit a transaction that comes from OX567, and it will go down this green path here to use the code that we write to handle the transaction according to the code that we wrote. So the reason this flow exists and a default account exists is because every transaction is handled according to smart contract code. If there is no smart contract code to handle it, it populates it with default code that acts currently according to how an EOA would act. Okay, so that's how you can submit a transaction from an EOA wallet, but the Abstract protocol actually has no EOA wallets in its kind of knowledge, right? It only knows smart contracts. And the reason this works smoothly with existing wallets like MetaMask and Coinbase wallets is because you can still submit a transaction with all of the fields and a signature that you would typically sign a message or a transaction with your private key, submit that to the protocol. It follows this path. There is no code deployed here because it's an EOA, right? My EOA doesn't have any contract code. So we reach the default account. Our transaction gets treated as if it was submitted from this default account smart contract. The default account smart contract, as I mentioned, treats everything as if it was submitted essentially by an EOA. So it literally checks the signature field as if it was an Ethereum transaction. It checks the signature field. Does that signature come from the public key that it's coming from in this from address? If those match up, then we can go ahead and execute the transaction. And I'll show you what that smart contract code looks like. One thing I want to mention is the default account and every account on Abstract has to follow a specific standard that is defined in an interface called the IAccount interface. So IAccount defines 5 specific functions that your account, including the default account, must implement, and it's what we're going to inherit and implement in this video. So IAccount is an interface that will import. It defines specific functions that we need to populate according to how we want our smart contract to behave. And then it's going to run through specific functions in order of validating the transactions, paying for the gas fees of the transactions, and executing the transactions, as we'll see as we build out the actual contract in this video. So hopefully that made sense. I guess the TLDR is the system contracts. They're special contracts deployed at Genesis to the protocol to handle specific things. 2 of those system contracts, one of them is the bootloader, which handles every transaction. And another one is called the default account, which is a smart contract built to behave exactly like an EOA, so that we have kind of parity, or I guess just an easy use of the chain with familiar methods like Coinbase Wallet and MetaMask Wallet, etc., for users to come in and use the chain easily without having to install any new extensions or anything like that for our crypto native users. And of course, there are several other system contracts. Some of them we'll touch in this video as well, but these are the 2 main ones that you need to keep in mind and understand as we move forward to build our smart contracts out. So without further ado, let's dive into our VS Code now and start writing out this smart contract. What you'll notice is if you jump into the node modules, you'll find the @Matter Labs folder. And I'll show you how to find this on GitHub as well. But just so it's easy, so you can find it locally, you'll see we have a bunch of the extensions installed. But down the bottom, we have ZK Sync contracts. And within here, within the L2 folder, you'll find system contracts. You can see here is bootloader utilities. We even have the default account smart contract. And this inherits the IAccount contract. So you can see this is coming from interfaces IAccount. You should be able to control click into this, but just in case you can't, this is actually coming from interfaces IAccount, and that is what we're looking at here. So as I mentioned, within this, each account in Abstract expects you to implement each of these functions. So we have validate transaction, execute transaction from outside, pay for transaction, and prepare for paymaster. So 1, 2, 3, 4, 5 functions that we need to implement as a kind of bare bones for our account to follow the account standard. If we take a look at the default account, you can see it has a couple of extra things, but it also follows each of these functions. So it has a validate transaction, it has some internal functions to actually perform the signature checking and things like this before running execute transaction. Execute transaction from outside is actually empty. And then if we scroll down, we have a couple of other functions like pay for transaction and prepare for paymaster, as well as fallback and receive, which we're also going to implement in our contract as well. So this is a good kind of a reference of what are the purpose of each of these functions. But as a general rule of thumb, the process that's going to occur can be simplified down to kind of 3 steps. So if you remember in our diagram, we had the bootloader transferring the transaction information to each of the smart contract accounts, which you can see in this transaction struct here. So what happens is in the kind of default flow, the first step is it's going to validate the transaction. And validate transaction is basically asking, am I going to execute this transaction? Like, do I want to deal with this, right? So in this function, you're going to say a couple of checks, right? You can imagine the extent that you could go to validate a transaction. Does it meet certain criteria? Is it below a certain spending limit? Does the signature match the account that is verified to make transactions from this smart contract, etc., etc. It's basically a set of rules that you're going to write to validate a transaction before continuing. So that is the first step. The second step is it's actually going to call pay for transaction. Now, I'm going to kind of skip over paymasters in this video, but an alternative is the gas fees are paid by somebody else, which that case, it would be prepare for paymaster. But the default case is this account pays for gas for the transactions out of the account itself. So this again receives the transaction. Basically, what we're going to do in this function is pay the bootloader the gas fees for the transaction. So first we verify it, validate, do we want to execute it? If we do, we'll continue to step 2, which is pay for transaction. Once we've paid the gas fee to the bootloader, we'll continue to step 3, which is execute transaction. So those are the 3 functions that you really need to care about: is validate, am I going to do this? Pay the gas fee in order to actually do that transaction. And the third step is literally just do the transaction. So it's actually not that complicated. It's basically saying, am I going to do it? Pay for doing it. Actually do it. So it's actually quite simple once you break it down. The implementation details we'll go through, of course, when we actually build it out. But what we're going to do is inside of our contracts folder, we have our greeter. What I'm going to do is just go ahead and replace this greeter smart contract with an absolute bare bones implementation of this IAccount interface that all smart contract accounts need to implement inside of Abstract. All right, so let's get started actually writing our smart contract. Firstly, let's just go ahead and nuke all of the contents of the contract itself. We'll rename the contract to basic account, and then we'll actually rename the file here to basic account as well. Now, to build an account that follows the smart contract account standards on Abstract, we need to implement that IAccount interface. And what we're going to do first is we're going to go ahead and actually import that from node modules here. So you don't have to find it in node modules. You can just import it from the documentation or wherever you have it handy. Basically, I'm just going to do this to show you where it's actually being pulled in from. So underneath ZK Sync contracts, L2, system contracts interfaces, you'll see the IAccount that we were looking at. So I'm just going to copy the relative path, and beneath our Solidity version definition here, I'm just going to say import that and remove the initial node modules here. So now we're importing this, and it has a red underline because we have the slash at the front, sorry. So now if we command click into it, mine's just kind of bugging out with the extension. But if you are able to command click into it, that means you have successfully installed, and that red underline should kind of resolve itself. Then what we're going to do is we're going to inherit that IAccount. So we're first going to say basic account is IAccount. And we'll just give our thing a quick little reload here to just make sure our red underline goes away as it should. And there we go. As you can see, now our import is fine. I'm not sure what happened there, but it's saying it should be marked as abstract. And if you've ever written a smart contract that inherits something else before, you should know, hey, that means I'm not implementing the expected functions that this interface has. So what we need to do now is basically say, well, in order to obey by the rules of this interface, we need to inherit and implement each of these functions here. So what I'm going to do, just to keep it simple, is literally just copy paste each of these functions into our smart contract here. And instead of these semicolons, so I'll go ahead and select all of these by holding Alt and click. Instead of these semicolons, we'll make them empty functions. And then within that function, we'll say to do, we need to implement this. So right now, our contract does satisfy the criteria of this interface, but we actually need to write the logic of each of these functions in here. Cool. So if we jump into our terminal, what we should be able to do is run npm run compile, and hopefully it's all good in the green because we technically have implemented the interface. It just doesn't do anything. So let's see what our compiler comes out with here. And as you can see, it does compile successfully. So we have actually technically implemented a smart contract account on Abstract. It just does nothing. So just to clean this up, I'm going to go ahead and delete all of these comments that came with the copy paste here. And as I mentioned, the steps that are going to occur during the default flow is one, do I want to execute this transaction? And basically how this works is if you do, return the magic value. And we're going to go ahead and import what that magic value is. But you can see here, this function expects you to return a magic value. And if that magic value is set to something specific that we're going to import, then it basically means, yes, I want to continue to execute that transaction. What's going to happen next, and I'll move this up just to make it simple, is step number 2 is we're going to actually pay the gas for the transaction. Once we've paid the gas, we then move on to step 3, which is actually execute the transaction. And these we're going to talk about later, but these 3 functions are the ones we care about the most at the kind of core of our smart contract. So now will be the time to get as creative as you want, come up with any cool custom ideas that you want to build into your smart contracts. But what I'm going to show you is some of the default behaviors from the default account, and we'll import the most bare bones kind of implementation that we can to move on to how to deploy the smart contracts and interact with them to submit transactions as if they were coming from the smart contract accounts that you built. So you can come up with cool ideas, or you can continue to follow along with what I'm going to do in this video. What we're going to first do is open up the default account, see how that behaves, and then kind of mimic the bare bones implementation into our smart contract first. So without further ado, let's continue. All right, so now let's go ahead and take a look again inside of the dependencies we have here. We're going to jump into default account.source. So here is a path at MataLabs, ZK Sync contracts, L2 system contracts. And if we take a look, first, we are importing a couple of things. We're also going to import these into our contracts. We then set using transaction helper for asterisks. We're also going to do that. Define some modifiers like only accept transactions from the bootloader. We will also implement that. We're going to skip past this delegate call section here. And then we jump into our first step here, which is validate transaction. So all we're doing here is saying only the bootloader can call it. And I want to return either a value of 0. So that basically says don't continue with the transaction, or we want to return the magic success value here. So account validation success magic. And this is coming from the IAccount interface. So we've already imported that, but basically it says if you return this, you're agreeing to continue with the rest of the transaction. And I'll let you read through some of these here if you want to. Basically, this is the default behavior of the default account that acts exactly as if it were the EOA. So it basically checks, I assume, some of the signatures. I haven't actually looked too deeply into what's going on here. We're just going to skip past this and simply let anything go ahead. So all we're going to do is return the magic value here. So we can actually go ahead and implement that now. If we copy this line 102 here on validate transaction in our smart contract, all we're going to do is return this magic value set to account validation success magic. And that literally just says, hey, I'm going to agree to run any transaction from anyone. Obviously, you wouldn't want to do this in the real world, but just to show you, you can literally put anything you want in here. You can accept any transaction, you can deny every transaction, you can customize every aspect of when a transaction should go through when it hits this function here. Now, the one mandatory rule that you must do inside of validate transaction is actually increment the nonce of the account. And you can see that's exactly what's going on here. So you can see the nonce holder can be called with the isSystem flag, and we'll talk about what that means shortly. But basically, we just need to handle the nonce, and we can go ahead and copy paste that into our function here as well. Whoops, I copied it twice. We just need it once. So basically, step 1 is handle the nonce, and then step 2 is do anything else you want in here. I'll leave that up to your imagination. And then step 3 is if we want to continue, return this magic value. All right, so now you can see we have a couple of issues here related to calling things that we haven't imported. So from the default account up the top, you can see we have imported a couple of things like the nonce holder system contract and the system contract helper. Again, there is another system contract related to handling the nonces as well. I won't go too deep into that in this video, but basically we need to import the stuff that the default account is calling if we're going to copy and paste this logic across. So instead of showing you, I think you're pretty sick of me jumping into the node modules here. I'm just going to go ahead and copy and paste each of these into our import statement here. And obviously we don't have a libraries folder or a directory here because inside of this dependency, they have the libraries directory. But what we need to do is replace the // in each of these. So I'm going to go ahead and select here, here, and over here. We'll delete these sections, the // and what we're going to replace it with is at MataLabs /ZK Sync contracts /L2 system contracts / And now we are good. We have imported each of these. You can click into all of them. And I believe we don't need this efficient call. We're not going to be using that inside of our smart contract here. And we also don't need this deployer system contract here. One final thing we're going to copy is this line 19 from the default account to specify that we want to use this transaction helper library. So we'll paste that underneath our smart contract definition here. And since we're not using these variables, we can safely remove the names of those variables as well. Okay, so that is completed our validate transaction function. So basically we increment the nonce of the account. So all this code is saying is call with propagated revert. And as you can see on line 25 here, it just calls increment min nonce if equals on the system contract related to handling nonces. So basically grab the system contract for nonce handler, and you can dive into what that looks like if you choose to, and increment the nonce of this account. So I'll actually just minimize that because it's not really that relevant to what we're doing here, but this is just the only mandatory requirement that you must implement in validate transaction. And then you're completely free to add any rules that you want. You can read any state, write any state, do anything you really want inside validate transaction. And then finally, if you choose to go ahead with the transaction, if you want to continue, return this magic value down the bottom. So hopefully that makes sense. All we need to do, handle the nonce, do anything else. If we want to continue, return that magic value. So once step 1 completes, I'll go ahead and minimize this now. Then we're going to continue into step 2, which is to actually pay the gas for the transaction. What we're going to do for this function is take a look at how the default account handles it again. As you can see, all it does is call pay to the bootloader. And essentially that's saying, well, pay the gas fee for this transaction to the bootloader. So we're going to go ahead and copy and paste this into our basic account as well. So let's remove this to do comment here, paste this into our smart contract. And since we're not using these variables here, we can go ahead and remove these as well. Easy. So now we've checked, do we want to continue with the transaction? If we do, by returning that magic value, let's continue, pay the gas fee to the bootloader. If the bootloader is satisfied, it's going to continue on to step number 3 here, which is actually executing the transaction. So if we again take a look at the default account, you can see it's calling this internal function called _execute. Now this is basically saying if it's a deployment transaction. Abstract also handles deploying contracts a little bit differently from Ethereum. We won't get into that into this video, but if it's not a deployment contract, then it uses this efficient call library to actually call that transaction as well in an efficient manner. So it's a little confusing what's going on in here. I won't go too deep into it in this video. You can dive into it yourself if you choose to. Basically, all we want to do inside of execute transaction is literally just run the logic and execute the actual transaction. To do that, the first thing we're going to do is grab this address of where to send the transaction to. So we're just doing some conversions into the format that we need out of the transaction that gets passed in here. Once we have where we're sending it to, we're literally just going to call the transaction. So send it to this address by passing .call here, provide the value of the transaction. So how much do we want to include in actually sending this address here as part of that transaction, and then forward on the data as well. And we'll just grab the Boolean value of success of whether that resulted in a successful call or a failure. And then with this success variable, all we're going to do is say require that the success was true. Otherwise, we'll revert with this message saying failed to execute the transaction. So again, this is very simple. Probably don't want to have this basic of an implementation in a real smart contract, as it's not going to handle anything like deploying smart contracts properly as it does in the default account. So you can always refer back to what the default account is doing and kind of adjust your smart contract accordingly. I just wanted to show you a very basic implementation of what this looks like so you can go ahead and build out your own. And again, just like the previous one, we can go ahead and remove these unused variable names and save our smart contract here. And believe it or not, that is actually the bare minimum you can do to implement this IAccount that actually works, right? It's actually going to validate the transaction. Of course, we are just literally accepting anything, which is kind of funny. Anyone can use this account to send transactions. So that's kind of funny, but also stupid if you were to deploy this with any real funds. So that's why we're staying on a testnet And of course, this is not a really valid or a viable way to implement this. Once it is validated, we pay the gas fee to the transaction. So that is simply sending it to the bootloader. And then finally, we execute the transaction. So again, this is not recommended for real accounts, as it's going to run into a lot of edge cases and fail, like deploying smart contracts. But for this video, we're keeping it as simple as possible. So we'll close that function, sorry. And then what we have here is execute transaction from outside. So again, I'm not going to go too deep into this video. You can read the default account implementation for notes on what this is, but you can actually just leave this as empty, as I believe the default account does. This is related to handling transactions from L1 to L2, which I won't get into in this video. Then that leaves us with the paymaster flow. So we're not going to implement paymasters in this video. It'll probably be a follow-up video, but for paymasters, we actually simply call a function on the transaction. So it's going to be underscore transaction dot process paymaster input and provide, I don't even think we need to provide the transaction in here. Yep, and then we can safely delete these unused variables just so our compiler is happy. And now we have support for paymasters. Again, we'll go into more detail in a future video, but the TLDR is that the accounts have support for paymasters, which means someone else can pay the gas fee instead of you paying the gas fee in step 2 here. But we won't go too deep into implementing that in this video either. One final thing that we'll notice in the default account, if we open that back up, is that beneath these functions, it also has a fallback and a receive function. So I'm going to go ahead and copy paste those beneath our functions here. So you can see we have the fallback and the receive of what to do when the contract is called directly and what to do if we hit this fallback state as well. One other thing you'll notice that we missed is this modifier here that is on each of the functions called ignore non-bootloader. So here we have, this is on validate transaction, it's on execute transaction, it's on pay for transaction, it's on all of them, right? So basically we're going to, it's on all of them except for nope, it's on all of them. Okay, so basically we're gonna go ahead and copy paste this modifier into our basic account, paste that in here. And then on each of the functions, so I'll select here after the payable on each of these. So 1, 2, 3, 4, 5, and we'll add that only, what was the name of it? Ignore non-bootloader modifier here. So I don't think we need the open parentheses. So now these functions will only be able to be called by the bootloader. So basically this is checking if the sender of this transaction was from the bootloader, then we run it. If not, then we do not run this transaction. So only the bootloader can call each of these functions for us. One final thing I will call out now, because we're going to run into it later in this video as well, is that in order to call the system contracts, you can see on line 81 here, we need this system flag to be true. Now we can configure this inside of our hard hat by jumping into, if we exit out node modules, jumping into hard hat, and underneath the zk-sulk settings here, you can actually set is system to true. And this is actually going to give you a flag that this name is deprecated. So just in case you're watching this from the future, the new name for this flag is enable error VM extensions. So that's all we need to do in order to actually successfully make sure that our validate transaction here is going to be able to call the system contracts. We just need to set that is system flag to true, as it says to us in the documentation of the default account. One more thing that we need to do before we go onto that 3-step process that we showed earlier in the video of cleaning, compiling, and deploying, and then the 4th step of interacting, we actually need to modify the deployment script. So if you jump into the deploy directory, deploy, and you'll find this function called deploy contract coming from utils. So that is actually within this utils.ts folder here. And there is a function called deploy contract. Now, within this file, or this function rather, if we scroll down to the part where it says deploy on line 99 for me, you can see this optionally includes a deployment type. So deployment type, if we click into this function and we look at this type here, you can see there is create, create account and create to account. Now we won't go into what create to means if you don't know in this video, but we're concerned with the different deployment types. So when you deploy a smart contract account, it actually has a separate type of deployment. So we're going to need to provide create account rather than create for the deployment type in this video. So what you can do is in deploy, in this line 99 here, you can just provide, you can see the different options here. I'm just going to provide create account. Now, what I actually would recommend that you do is provide this as a argument here. So instead of just hard coding, because if you go to deploy an actual smart contract that is not a smart account and you use this same script, it's going to bug out because you're not deploying a contract. You're not deploying an account, you're deploying just a regular smart contract. So just keep that in mind if you're using this utils file for multiple different contracts that are not just accounts. For this video, we'll just hard code it in here because we're only going to be deploying the accounts. So we're safely just assuming that everything that we're running through this function is an account smart contract. Okay, so now what we're ready to do is run that 3 or 4 step process of clean, compile, deploy, interact. So what we're going to do is we're going to jump into this deploy/deploy.ts file here. And you can see this is still hard coded to be the greeter smart contract. So we'll delete that comment. And what we're going to do is instead of greeter, we're going to deploy our basic account smart contract here. So we'll rename the greeter with basic account. And since there is no constructor, we don't need any constructor arguments. In fact, we can actually just get rid of this altogether. So now we have the name of our contract, and we can just even make this simpler, put it in one line and deploy contract basic account. So very, very simple. Basically, it jumps into this file that we were just looking at and deploys our smart contract. All right. So if we run npm run clean now, give us a clean environment to compile from. We'll run npm run compile. This will go ahead and recompile our smart contracts. We shouldn't see any errors that I'm hoping for our video here. Yep, there we go. Have a couple of warnings on some dependencies, but that is fine. So then what we can do is npm run deploy. And this is going to rerun our deployment script. So you can see now instead of greeter, it starts the deployment process for basic account, gives us a nice little estimation of how much this is going to cost, and then outputs the contract address. So if you remember from the first kind of portion of our video, the flow after that 3-step process was to replace the contract address on line 6 here with the new contract address. So now when we run this interact script, it's going to call the function with the smart contract address that we just deployed. And you're going to have to kind of readjust that every time you recompile and redeploy your smart contracts within this file. So again, this is kind of hard coded to interact with the greeter smart contract. So what we're going to do next is change this to actually submit a transaction that interacts with our smart contract. So since this is built to interact with greeter, we can actually just kind of nuke pretty much everything in here except for this first console log. And I don't believe we'll need we will need ethers, so we'll leave that there. We won't need HRE, and we will need the get wallet function here. So just as some comments before we actually write this, I want to explain what we're doing, and it's kind of related to the diagram that we presented earlier on in the video, the flow that we're going to go through here. So what we're doing in this function is first, we're going to actually create an object that represents the transaction we want to send, because over the RPC, we need to submit a transaction object that contains things like where the transaction is going, who the transaction came from, things like the gas limit, the nonce, all of the stuff that you'd expect to see from a transaction that gets sent on Ethereum. Second, we're going to broadcast the transaction to the network. So basically step 1 is to actually create literally a JavaScript object with all of the required fields for a transaction to be valid. And this is going to follow the EIP 712 standard here. And we'll talk a little bit about what that means. I don't want to go too deep into it, but we're going to generate it in a specific way. And then we're going to actually broadcast it to the network via RPC. Now, what's pretty interesting and confusing at first about this step is we're not going to send it from a wallet. We're going to send it just straight to the RPC. It's not coming from a wallet. And that was kind of what we talked about in the diagram at the start, is it doesn't necessarily have to come from a wallet. It just has to go via the RPC and hit the chain, and therefore hit the bootloader of the chain. So the first step within that, once it reaches the chain, is it's going to get picked up by the bootloader. The second step here is that the bootloader reads each of the transactions. So it kind of batches them and does a couple of other things as well, but it batches the transactions. And for each of those transactions, it reads the from field, which is where the transaction came from, but not necessarily, which is kind of confusing because in the script that we're going to generate, really, we can put the from address to whatever we want. I could say you submitted this transaction, or I could say anyone else submitted the transaction and broadcast that to the network. Now, what is going to happen then, if you've been following along with the smart contract, is it'll hit the validate function. And likely, if you built a sane smart contract, not that we have, it's going to say, well, I've checked the from address and I've checked the signature and it doesn't match up. So you obviously didn't send this. But in our case, our validate function just accepts anything, right? So it will literally just pretty much not care about anything and go ahead and say, yeah, whatever, I'll submit that transaction to be executed. So basically what I'm saying here is the from address isn't actually necessarily where the transaction came from. And since we're not sending it from a wallet, what is the from address? And hopefully you know the answer to that question, but if you don't, we'll write it out in this function shortly. Well, the answer is actually here. I didn't read my next sentence, but we're going to send it to set that field to the smart contract account that we deployed. So I kind of spoiled it there, but hopefully if you got that answer right, we're going to set the from field, or AKA who sent this transaction, to the smart contract that we deployed, our smart contract wallet here on line 5. Which will actually become line 7 after our imports here. So let's just say line 5 for now, and that's going to become line 7 later. And then step 3 is that the smart contract account, aka the smart contract that we just wrote up, is going to run its 3 functions in order. So first, validate transaction, and maybe a little quiz if you pause the video of what's going to come next in B and C. If we first validated it, secondly, we pay for the transaction, and finally, we execute the transaction. So this is going to be a little weird. I'm going to kind of write this function in reverse, but hopefully it makes sense why we're doing it that way. I think it actually makes more sense to write it kind of from the bottom up than what the code is, because it is a little messy the way that we format and generate the transaction that we're going to broadcast. So what we're going to do first is we're actually just going to log out the transaction that we send at the end. And again, I'm kind of writing this from the bottom up. I know it's a bit weird, but hopefully it makes sense why we're doing it this way. So what we're going to do is at the end, we will have broadcasted a transaction to the network with this transaction variable containing the details of that transaction. Above that, we're going to get the provider, and hopefully you remember as we import this from our utils file up the top on line 1 here, this function basically connected to the network. So this is reading from the hard hat config file, and whatever the default network is, it's going to grab the RPC URL and connect as a provider to that network so that we can read and submit transactions to that RPC. So basically what we're doing here is we're getting the RPC and we're broadcasting a transaction to the network via that RPC. And then now we have this variable sent transaction here that will contain all of the information of the transaction that we broadcasted. Within this broadcast transaction function of the RPC, it accepts a string of a signed transaction. So what we're going to do above this is create an object representing a transaction with all of the fields like the to, the from, the gas limit, etc., that you'd expect of a standard transaction. And we're going to just serialize it, which basically just means convert it into a string so that we can pass it into this broadcast transaction function here. So to generate the transaction, basically what we're going to do here is we're going to say const serialize transaction is equal to serialize EIP 712. And this is coming from ZK Sync ethers. So up the top here, we've just imported serialize EIP 712. I'm just going to move that down to line 3 here. And that is going to allow us, if we click into this, as you can see, the details of this is serializes an EIP712 transaction that we can provide all the details of what we want to actually include as the details of that transaction. So that accepts a transaction object. And here, if we ask what it expects, you can see all of the stuff you'd expect of a transaction. So the reason I did this in reverse was I don't want to sit here and provide an access list. I don't want to provide the chain ID. I don't want to provide the data. Don't want to provide the gas limit. I don't want to provide the gas price, etc., right? Some of the stuff I want to provide, like, for example, where the transaction came from, I want to specify that to be the smart contract account on line number 6 here. I also want to specify what the transaction is. I think we're just going to send some small amount of ether to a different account for this basic example here. I also want to make sure I include some custom data, as we'll walk through what that means in order for this transaction to even be accepted here. But I don't want to sit here and waste your time setting the gas limit, setting all of the extra stuff for the transaction. So we're going to kind of do a little hack above this, but I didn't want to do that first because it is kind of confusing if you don't have the context of why we're doing that. Okay, so within this, we're first going to provide the nonce, and we're going to set that to 0. That is one thing that we actually do want. Importantly, we're going to set the from address to the smart contract address that we deployed, okay? So as we send this to the chain via the RPC, we're saying this contract is who's sending the transaction. So the contract is initiated by if we jump back into the terminal, the smart contract that we deployed, which is our basic account smart contract that we wrote. So this is who we're going to set the transaction to be coming from. So we can paste it in here, or we've actually stored it in this contract address field here. So we'll just paste contract address as the from field for this transaction. If we hover over this method, I guess, serialize EIP712, you can see it actually throws an error if custom signature is an empty string. So what we need to do is actually just custom data and pass a custom signature here. Now we can put an empty string that would cause an error. So let's just put something stupid in here like OX69 just to make sure that is happy, because we're literally not doing anything with this custom signature here. We just need to make sure it is provided when we call this function here, because if an empty string, then this function is actually going to error out. And you can see the details of this here, custom signature used for use cases when the signing's account is not an EOA, which is what we're doing in this case. If we again take a look at this serialized EIP712, you'll see if chain ID is not provided, it will fail as well. So let's go ahead and just hard code the chain ID. The local node address you can actually see inside of Docker. If you go into the logs at the very first line, you can see it is set to 260. Not that that's really that important. We're just going to hard code chain ID to be set to 260 for now. And then if we jump into our terminal, we run npm run interact. Even though the TypeScript passes, it's missing some fields like to address is null. So if we go ahead, jump into the serialize function here again, let's say to address is equal to, we'll go ahead and import the rich accounts and we'll grab random one out of those. Let's just say index number 3. And then we rerun the interact command. We're going to see again, well, now I need to hard code the gas limit or the max fee per gas. And pretty much what you'll do is you'll go back and forth between your VS Code and your terminal to say, well, this worked. And well, now it's it's asking me to add a new field like gas limit, and it's asking me to add a new field and a new field, and you'll keep going back and forth. An easier way to do this is just generate a fake transaction object and provide all of those fields like the gas limit, the gas price, max fee per gas, all of the stuff that you don't really want to hard code in here. It's easier to just create a fake transaction from a void signer is the way that we're going to do it, and provide those fields and override what you don't want. So let's go ahead and remove that from here. We'll remove the chain ID, keep it as clean as possible. These are the ones that we actually need to care about, and we will go from here. So hopefully now you understand what we're about to do. Basically, we just need to create a dummy transaction object. And thankfully in Ethers, there is this concept of a void signer. So basically what we're going to do here is we're going to copy and paste this in. The transaction generator object is what I've called it. And we'll go ahead and import void signer from Ethers on line number 2 here. A void signer, as it suggests, is basically a signer that allows an address to be used in an API which accepts a signer, but there are no credentials to actually sign anything. So it can't actually sign stuff. It's just helpful for us to create a transaction object. So that's what we're doing. And then what we can do beneath that is we'll say const transaction fields is equal to transaction generator dot populate transaction. And within here, we can provide any fields that we want. Only thing we need to provide is actually what the transaction is. So for us, we're just going to send a dummy transaction to that rich account. So local rich wallets number 3 dot address. And that is all we need to do. So now we have a transaction. I think I might need to await this because it is async. Yeah, so now we have transaction like, and we can see on that transaction fields object, we have the gas limit, we have the gas price, we have all of the stuff that we don't want to hard code, and that is actually being pulled in from the specific chain that we're using inside of our hard hat config. So when we do it now, it's going to be set to figure out what gas do we need for the local chain to actually get this transaction to go through. So we don't need to figure out and hard code it inside this 712 object here. So final step to that is you just need to spread in all of the fields. So this is a JavaScript syntax to say, take all of the fields of this object and pass them into this. And then anything after that point, you override. So overriding where the contract, where the transaction came from and all the stuff that we said before. So the reason we did it this way, and I know it's kind of ugly, is we just want to generate a dummy transaction object with all the gas limits, all the stuff that we don't want to hard code. And then the stuff that we do want to set, we actually provide it in here. And then we broadcast that transaction. One thing I quickly just realized is we're actually not transferring anything to them. So we're just sending a message, which I guess is fine. We could still go ahead with this, but let's set a value of to ether, pass ether, I think it is, pass ether, and that is imported up on line number 2. Let's do 0.00069. Actually, let's change that so it's not confusing. 420, and that is going to pass or send that amount of ETH to that wallet address, just because we were actually sending them nothing. Just to summarize what we've done, we are generating a transaction and we're going to submit that via the RPC to the chain. And in this case, we're going to do it locally to the one running in the Docker container. But after that, we'll do it to the Abstract chain and actually show you exactly what that looks like on the Block Explorer as well. Awesome. So jumping back into the terminal, now we should have successfully resolved these errors. Let's run the interact command and we get another error. And I was actually expecting this, despite my Pikachu face right there. This is because, well, hopefully you can guess why this is actually, because the account that we're sending it from, I'm not sure if it says where it's coming from in here. It doesn't look like it, but the account, the smart contract that we're sending it from doesn't have any of the, doesn't have any balance because we just deployed it with no balance. So therefore it can't pay the gas fee for the transaction to the bootloader. So on our VS Code, if you remember inside of our basic account, in the pay for transaction, it calls pay to the bootloader based on how expensive that transaction is going to be. However, our account doesn't have any money basically on the account. So all we need to do is just supply a little bit of gas money to the smart contract that we deployed, and then we can rerun this interaction here. So to do that, we can just say const load funds is equal to await get wallet dot transfer. And within this transfer, we're going to provide the amount and we'll do pass ether. How much do we want to do? 0.001, that should be good. And then 2 is to the contract address. So we're just going to actually load some funds. We don't even need to store that in a variable. Just load a little bit of money before we actually go ahead and send the transaction from our account. So let's try again from our terminal here. Clear this out and then run npm run interact once again. Let's change what account we're using. So let's grab a new fresh account from here. Let's just say this one, and within .env, again, this is not a real private key. This is one of these. demo accounts, local rich wallets. So I just grabbed a random one from there, and let's see if it was an issue with the wallet. So let's run npm run interact, and okay, reusing the same nonce twice. That's a new error. So let's increment the nonce back in our VS Code to be 1. We'll set this npm run interact again, and looks like we were successful. Okay, so running script to interact with contract 4B5D, which was our contract address here. So it is successfully interacting with the right one. And the details of this is it's a type 113 transaction, which is an account abstraction type transaction on Abstract. The nonce was 1, and the from is the smart contract address. Excellent. All right, so this transaction is actually coming from our smart contract wallet. So we successfully sent it to a random account. We sent it from our smart contract wallet. The data was nothing. The value was that 420 number that we put in to transfer them. The signature, as you can see, is actually nothing because our smart contract actually just accepts anything and approves it and goes ahead with that transaction. You can see all the stuff that got populated, like the gas limit, the gas price, max priority. You could hard code all of this stuff, but we just chose to kind of abstract it away with this populate transaction stuff here. But this is excellent. This is actually successful. We have officially initiated the transaction from the smart contract account that we've deployed, and it sent a small amount of ether to a different account, and that came from our smart contract wallet. So we've successfully implemented a native account abstraction account and transferred some funds from that account via this transaction here. What we're going to do next is actually deploy this onto the Abstract testnet and show you what this looks like from the Block Explorer perspective. So to do that, you'll first need to grab some funds onto the testnet, which I'll show you how to do. And then what you'll be able to do is actually submit the same script. We're just going to input the network information for the Abstract testnet, point our script to the Abstract testnet. We'll redeploy the smart contract onto the testnet, run this transaction onto the testnet as well, and then we'll show you what it looks like on the Block Explorer. All right, so if we go back to our VS Code, we can get rid of these options here. So we don't need the Dockerize node, we don't need these ZK sync networks. We're going to add in a new entry for our Abstract testnet. So we'll say Abstract testnet is equal to, and what we're going to put in here is the URL, which is this value. We'll also put in the ETH network. So this is the L1, since Abstract is an L2 and the testnet is built on top of Sepolia. The ZK sync flag is set to true. And here is the verify URL. We just need to add a little comment here. And this is, of course, all available on the Abstract documentation as well, if you prefer to just copy and paste that in. This verify URL is required to actually upload the source code so that we can see the contract tab on the Block Explorer as well. Then what we're going to do is we're going to swap the default network from our in-memory node to the Abstract testnet. Now, in order for this to work, you'll need your env private key, as I'm exposing here because this is not mine. This is one of the rich accounts that come default with the project. What I'm going to do now is I'm going to get some testnet funds on the Abstract testnet and replace this wallet private key with a test account that only has test funds and no real funds. And then we'll redeploy the smart contract and rerun that interact script pointing to the Abstract testnet. Inside the documentation, which will be linked in the description as well, if you can't find it, it's docs.abs.xyz. The bridge tab here, you can see we have the native bridge and the relay. I'm sure this will change a lot because this is a very first kind of version of our documentation, but the concepts will still be the same. You'll be able to access the native bridge, which will take around 15 minutes. You'll also be able to access on relay as well, which will provide some faster ways to actually bridge for a small fee. But since we're on a testnet, it doesn't really matter about those fees. One thing you can do is head over to the thirdweb.com/abstract testnet page and grab some free testnet funds, and those will be sent to your wallet directly. As you can see, I now have 0.1 on the abs testnet. So we're ready to use this wallet, which again has no real money associated with it. You can see I have 0 ETH on ETH mainnet. This has 0 real funds associated to it. What I'm going to do is I'm going to export my private key from this wallet. Again, this is not best practice. You should not use this flow with any real money. So we're just doing this on testnet. And of course, I'm doing with a demo account that I don't really care about. So here I'll go ahead and copy my my private key, and then inside of our VS Code, I'll replace this with the private key that I just copy pasted. I will do that off screen so you don't see my private key. You should never expose any private keys. Get into the practice of doing that. And now my private key file is configured to be an account that has funds on the Abstract testnet. So then what we can safely do now is, since we have some funds, I have this npm run deploy script, and you'll notice now it's taking the basic account, and the balance is actually too low to even deploy onto the testnet right now. Seems like the gas fees are a little bit high for some reason, but let's go ahead and grab a little bit more test funds and come back to this. Just to show you the native bridge, since we don't have enough money as well, I'll go ahead and show you the native bridge interface to actually bridge some funds across from the testnet. Go ahead and connect my wallet with Coinbase here. Connect. Beautiful. All right, we are connected to the testnet. Since we're bridging from L1 to L2, I have one Sepolia testnet, so I'll transfer let's do 0.25 across to the testnet. We'll continue. I understand. This is on the testnet, so I don't really care about these funds. Go ahead and bridge now, and you can see it's going to take around 15 minutes for these funds to go through. Go ahead and confirm this in the wallet request here. Seems like the testnet fees are absurdly high for whatever reason right now, but that won't be the case in your run through. So you can see on the native bridge as well, our transaction is complete. So it was even faster than 15 minutes. And our balance here should update in just a moment. There we go, 0.35. So we should have more than enough. I mean, you shouldn't need close to this amount. It just seems like the testnet is going through a period of high fees right now for some reason. So if we jump back into the terminal, if we rerun the same command, npm run deploy, start the deployment process. This one costs 0.1, which again is pretty high. It should not even be close to this in your case. It just seems to be happening at my, of course, in the demo. So you can see we've successfully deployed it at this contract address onto the Abstract testnet. And now we're going to go ahead and verify that smart contract. And this is successfully verified. So let's copy the contract address. We'll jump back into VS Code. And you remember in the interact script, let's replace line 6 with our contract address here. And one other thing you might need to change is inside of the interact script down the bottom here, you might want to set nonce to 0 from a fresh account. I did run into some issues with this. I guess you need to send sequential nonces like nonce 0, nonce 1, nonce 2. So you might need to just update this every time you run the interact script, depending on when you're watching the video as well. So here we go. All right, we now have this contract address. If we again go to the documentation for Abstract, and if we check the block explorer link, you'll be able to see explorer testnet.abs.xyz. If we paste this account in, we can see it was created not long ago, and as basic account. That is because of our verification step. We can see inside of the contract all of the code uploaded and verified. So now let's go back to our VS Code. What we're going to do is we're going to send this amount of ETH, and let's lower this by a lot. Let's say 0.01 ETH for the gas fees, because I don't have that much test funds to play around with. And then we'll transfer that amount of money just the same. So we'll change a little configuration with the gas, and then we'll run back into the terminal, run npm run interact. This is going to send it to our 6A9 smart contract address, and the transaction was sent. It's not necessarily successful because we aren't actually waiting for it to be mined. We could add a wait under this 43, but I assume that it is actually going to work. So let's jump back into the block explorer here. We hit a quick little refresh, and beautiful. We see the two transactions. So we see the transaction come in. So that is us loading in the 0.01 inside of this line here, load funds transaction. So that's just making sure it has enough funds to actually pay the gas fees. And then inside of this second transaction, let's click into this. But at a high level, you can see it transferred 0.00042 to one of those dummy accounts, the OXA1 or the rich loaded wallets. And this transaction came from our smart contract, the OX6A9. So that is this basic account contract here, OX6A9. If we go back into that transaction, it's coming from that account and it's going to some one of those rich local wallets. So that's pretty much just sending it to the abyss. It's just an example transaction. And the value is 0.0042. It validates the transaction, which really, again, just does nothing and approves everything, increments the nonce, and then goes through any custom logic that you implemented inside of this function, inside this account here, goes through validate transaction. It then pays for the transaction and finally executes the transaction in here. If we were to go ahead and try this out again, you might want to just increment the nonce here. And then let's say this time we send 696. And we shouldn't even need this load funds transaction anymore because it has enough gas fees to deal with these transactions now. So simply just transfer that amount of funds, send that transaction again, and maybe let's change the address that we send it to. So let's send it to this guy here, OX366, just to kind of make it clear what we're doing. Let's just hard code that in as the send address. We'll do the exact same thing, jump into the terminal, npm run interact with our smart contract. And again, we have sent that transaction. Again, it's coming from our smart contract to OX366. Let's check in our block explorer, go back into our contract OX6A9. And you can see now it is sending 000696. And we click into this, obviously it's going to come from our smart contract. So we're essentially initializing transactions from our smart contract, which I think is pretty awesome, having native account abstraction so obvious into the protocol and so elegant from the block explorer as well. Awesome. So you can see we sent 696 to 366, which is the contract, the address rather, that we pasted in from local rich wallets. And that is it from the block explorer side. So if we go back to our little diagram here, you can see we submit transactions via that broadcast transaction request. Again, it's not coming from a wallet. We're literally just submitting it through the RPC. It has no signature on it. It's just an empty signature. It reaches the chain via the RPC, gets sent to the bootloader. The bootloader takes a look at the transaction and says, okay, the from address says it's coming from this smart contract account. I think it was like OX609 or something like that. And it sends it to that address here. And then it basically says, okay, well, now I'm here. Is there code here? And in our case, there actually is, because we deployed the smart contract called basic account and we verified it so you could actually even see it from the block explorer as well. And it goes down this green path here. So it says, all right, there is code here. Let me go down the green path and use that account's code. And for that reason, the transaction is accepted without any signature or with anything really to verify where it came from or any rules on what that transaction should do. Since our basic account literally accepts anything, it goes down this green path. The validation step returns the magic number, pays the gas fee to the bootloader for that transaction, the transfer that we sent with this RPC, and then it executes the transaction. And it just does that with the .call transaction that we wrote inside of our basic account. So with that said, hopefully you enjoyed this as much as I did making it. It was a lot of fun exploring the details of how Abstract implements this native account abstraction. It is a very unique feature, different from almost every other L2 in the space. And I think this is an awesome change that's going to enable a lot of unique use cases and helping new users onboard into the space as well. So if you enjoyed the video, please remember to leave a like and subscribe to the channel if you want to see more content like this. It does help me out in this world of algorithms that we live in to suggest, hey, I enjoyed this video, show me more of it. If you don't want to, that's also fine. If you got stuck at any point, again, there will be a link in the description to a Discord server where you can speak with other devs, speak with myself directly as well to answer any questions that you get stuck on, and reach out to me to say, hey, this isn't working, this needs to change, anything that you get stuck on. Appreciate you watching, enjoy the rest of your day, and I'll see you in the next one.